Minesweeper is one of the most well-known and iconic single-player puzzle games. The objective of the game is to clear a rectangular board containing hidden mines or bombs without detonating any of them. The gameplay is simple. Click on a square to reveal whether it's safe or has a mine underneath it. Safe squares have numbers telling you how many mines touch the square. You can use the number clues to solve the game by opening all of the safe squares. If you click on a mine, however, you lose the game. Minesweeper has its origins in the earliest mainframe games of the 1960s and 1970s. The earliest ancestor of Minesweeper was Jeremy Ratliff's Cube. But the version we all know and love today first appeared in a game pack from Microsoft in 1990. A version of the game called Microsoft Minesweeper was released as a standard part of Windows 3.1 in 1992. This saw an explosion in popularity and awareness of the game, with tech bloggers and journalists calling it iconic, famous, and even the most successful game ever. Versions of the game continue to be included in standard installs of Windows up through Windows Vista in 2007, though in Windows 8 released in 2012 and later, it must be downloaded as an app from the Microsoft Store. So let's recreate this iconic game using C++. But before we begin coding, we must break down the game into simpler, easier to understand parts and recreate them one by one using C++. Minesweeper has basically remained unchanged since its introduction in the 1990s. While some game developers put their own visual twists on the game, its styles, and how it looks overall, the experience has remained somewhat the same ever since. Boot up the game from an application or online and you'll be greeted with a grid of squares. The size of this grid may vary depending on the difficulty you're playing or on the preference of who developed the version of the game you own. But the standard sizes are as follows: a 9x9 grid for the beginner's difficulty with 10 hidden mines, a 16x16 grid for the intermediate difficulty with 40 hidden mines, and a 16x30 grid for the expert difficulty with 99 hidden mines. For the sake of simplicity, we'll stick with the standard sizes for the three aforementioned difficulties. On the top left of the grid, there's a number denoting how many mines is left on the board, with this number going down every time the player places down a flag. And on the top right of the grid is a stopwatch which starts as soon as the player clicks on a tile and stops after the player has either lost or won the game. The player has two actions they can do. Click on a tile to reveal whether it is a safe tile or it has a mine underneath. If the result is the latter, the player loses the game and has to start again. If the tile is safe, it can either have a number displayed denoting the amount of mines the tile touches or be blank, indicating that the tile has no adjacent mines. The other action the player can do is place down a flag, which is done on all the tiles the player thinks has mines underneath. To win the game, the player must reveal all the safe tiles without accidentally revealing a mine. Now that we know all that information, we can do a slight recap of the things we need to accomplish and start coding. For the grid, we print a statement asking for the user to enter a difficulty level. They can enter 0 for the beginner difficulty with a 9x9 grid and 10 mines, 1 for the intermediate difficulty with a 16x16 grid and 40 mines, and 2 for the advanced difficulty with a 16x30 grid and 99 mines. Then, we ask for an input, and that input is set as level. If the level is set as 0, then the rows and columns will be initialized and they'll have a value of 9, meaning that there will be 9 rows and 9 columns, so it's a 9x9 grid. The mine value is set as 10, so there will be 10 mines within this grid, and the difficulty is set as beginner. If the user enters 1, then the rows and column are instead set to a value of 16, meaning that there is going to be 16 rows and 16 columns. The mine value is set as 40, meaning there will be 40 mines in the grid, and the difficulty is set as intermediate. If the user enters 2, then the rows will be set with a value of 16 and the columns will be set with a value of 30. That means there will be 16 rows and 30 columns, making a 16x30 grid. The mine value is set as 99 and the difficulty is set to advanced. And this code at the bottom is to ensure that the user does not enter anything other than 0, 1, and 2. Now that the difficulty is set up, let's move on to how the game board, tiles, and mines are initialized. The code we did utilizes two game boards, a front board which the player interacts with and a back board which they cannot see. But why two boards?
The front board is the game board that the player interacts with. Here they can choose to reveal or flag tiles. The backboard stores the arm tiles and safe tiles with a corresponding number of adjacent mines. The backboard is basically the answer sheet, where the actions in the front board are compared to the backboard to determine whether the moves are valid, safe, or game ending.
Thank you for that explanation. Now, let's move on to the tiles. The number of tiles set on the board is dependent on the number of rows and columns, which vary based on the difficulty level that we set up previously. The more rows and columns there are, the more tiles there are. These are both set up in the front board and the back board. After the tiles have been initialized, the program then sets up the mines on the board. This is done randomly through this function, which selects a row and column to place the mine at random. The mines are placed on the backboard and are indicated by an asterisk. Then, these bool functions check if the given row and column coordinates represent an existing tile and if there is a mine in the given row and column coordinates. When you click on a tile in Minesweeper and it's a safe tile, then a number will appear in place of the tile you just clicked, which indicates the amount of mines that the tile is touching. In our code, instead of calculating this number as you play, this is all done as the board is initialized. This value is called mine count, and it is placed on each tile on the board. This starts at 0, and whenever the tile is adjacent to a mine, this count goes up by 1, and keeps going up depending on how many mines the tile is adjacent to. This is all done in the backboard, which the user cannot see. So whenever a player clicks on a tile in the front board and it is designated as safe, the number value or mine count from the backboard is then reflected on the front board. There is also another possibility when you click on a safe tile in Minesweeper, and that is that the tile comes up as a blank, meaning that there are no adjacent tiles that are mines. Blank tiles have a special property to them. When you click on one and there is another blank tile next to it, it is also revealed, and this process keeps on repeating until a number tile is shown. This is done through this function, which recursively reveals blank tiles by checking in all directions of the blank tile that was just clicked and repeats until it reveals a numbered one. Now, let's move on to the actions the player can take. This program allows the player two actions. They can enter 1 to reveal a tile and 2 to place down a flag. If the player types 1, then the tile is checked by referencing the backboard. If it is not safe, then the game ends. If the player types 2, then the tile is not revealed, but it is instead replaced by an exclamation mark. This indicates that the player has placed down a flag. If the player types anything else, then it is marked as an invalid input. Then the player is asked to input a valid one. The game ends when either the player clicks on a mine or the player has revealed all the safe tiles on the board. The time is then shown, which is indicated by a function that starts counting and incrementing by 1 per second as soon as the player selects a difficulty and ends when the player wins the game. This is then used in the leaderboard. Let's move on to the leaderboard, which is a simple text file. This function edits the leaderboard text file when a player wins any of the standard game modes and did better than the previous record holder. If there is no record, then the player's performance is automatically recorded. The user is asked to input a name, which will be reflected in the edited text file along with the time it took for the player to finish the board. Finally, this last bit of code is for checking if the player has entered a customized grid, which they can do so by typing in the command line. They can type in /minesweeper -r space followed by a number indicating the amount of rows they want to have, space dash C space followed by a number indicating the amount of columns they want to have, space dash M space followed by a number indicating the amount of mines they want to have. If the player chooses a custom grid, then the leaderboard does not apply to them.
And with that, we were successful in creating Minesweeper in C++. We faced some challenges, solved them, and resulted in this code which we are satisfied with. Thank you for watching.